This video is about a telescope built by my father, Jack Ells. It's a compact, well-balanced Newtonian reflector on an equatorial fork mounting. The head of the telescope can rotate, so the eyepiece is always in a convenient position. Its importance is that it's an automatic photometric telescope, or APT for short, one of the first of its kind. It required an initial half-hour setup using the button box seen in my father's hand. After this, it would be left alone all night under the control of a BBC computer to obtain the light curve of the chosen variable star. I programmed the computer. It worked using the most accurate method possible, by counting individual photons coming from the chosen target star. It was also very efficient, taking readings in less than a minute over many hours. On the left is a schematic diagram of the APT system. At the top is a BBC Model B microcomputer. Here's the telescope itself. It's a 212 mm diameter f4 Newtonian reflector. The stepper motors for right ascension and declination are also part of the telescope. The stepper motors need to be interfaced with the BBC microcomputer, but we won't look at this here. Here's the button box, which is only used during setup. The buttons control the stepper motors, causing the telescope to move in any required direction, either fast or slow. The yes and no buttons also help the user to control the setup. 3 pieces of equipment are needed to convert photons from the star to a count inside the computer. We'll look at how the signal changes at each stage A through D in the process. A. Photons from the star or some other target enter the telescope. They pass down a fluid light guide to the photomultiplier tube, or PMT. The light guide enables the signal processing to take place within the trolley. This is much better than having heavy and delicate equipment mounted at the eyepiece of the telescope. The diagram on the right shows how a photomultiplier tube works. It consists of several electrodes with a large voltage across them. When a photon hits the cathode, this causes an electron to be ejected. It's attracted to the dynode below. There's a cascade of electrons down the dynodes, and this generates an electrical pulse at the anode. This is shown schematically as electrical signal B. The job of the amplifier discriminator is to clean up this signal by squaring off the electrical pulses and removing the noise, and this is shown at C. The task of the counting board is to count these pulses under the control of the computer. D shows a count of 2, but in reality, for a reading lasting 40 seconds, say, a photon count of the order of several 100,000 is typical. Here's a glimpse inside the counting board. It's based on a design by John Watson. The large arrows show the data flow. Here's the layout of the equipment on the trolley. During an observing run, all the electronics are on the trolley in the shelter of a hut. Only the telescope itself is exposed to the elements. This shows the telescope once automatic observing has started. Only the fluid light guide and the leads to the 2 stepper motors are outside the hut. The first successful run of the APT was on the night of 1988, April 20th, 21st. It was an observation of the eclipsing binary star VW Cepheid. As might be expected, there were several mishaps along the way. Here are my father's notes. First, my father set the year as 988 rather than 1988. The telescope was pointing at the wrong part of the sky because of 1,000 years of precession. My father had to restart from the beginning. Automatic observing began. After about an hour, the results were degraded because of passing thin cloud. We had plenty of experience of this with our previous manual system. Next, there was a serious problem. The photon counts went to 0. My father put this down to a dicky connection in the electronics. Frustratingly, this problem recurred sporadically over the course of the next 6 months. We would try a fix and think we'd solved the problem, and then it would recur. Eventually, something we did corrected the problem permanently. My father restarted the program with false data, and so got a second and longer observing run. Here are the results. The first run shows the secondary minimum. At the end, there were spurious readings caused by thin clouds. Then the APT crashed. The second run shows the primary minimum, and the time of this minimum was obtained by fitting a least squares quadratic equation. The x-axis is time. It's marked in tenths of a day long ticks, and in hundredths short ticks. Times are corrected to be heliocentric. I won't explain this here, but Earth-centered timings can be early or late by up to about 8 minutes. The y-axis is delta magnitude. That is to say, the magnitude of the variable star minus the magnitude of a constant comparison star. This axis is marked by tenths of a magnitude short ticks. If there were a whole magnitude difference, there would also be a long tick. We can compare the APT with naked eye, or binocular or small telescope observations. On exceptional evenings, the APT can obtain a measured 5 millimag accuracy, and on typical evenings, 15 millimag accuracy is achievable. But with observations by eye, the notional accuracy is only 1/10 of a mag, and the actual accuracy can be a lot worse than this. The APT takes 40 seconds to take a raw brightness reading of a variable star. An observation made by eye takes roughly 5 minutes. The APT has to perform various other tasks, such as measuring a comparison star, or measuring the sky background, and so on. Despite this, it's ready to take the next variable star reading after 3 minutes 40 seconds. And it can continue in this way time after time. In contrast, to avoid bias when observing by eye, it's usually best to wait at least 15 minutes before repeating an observation. The APT can work throughout the night. On the other hand, it's difficult to observe variable stars by eye for extended periods. To do this for more than 5 hours is extremely challenging. Looking back at the light curve for VW Cephei, we see that it is a difficult target for naked eye observers. It varies by only 4/10 of a magnitude in total, and the difference between the primary and the secondary minimum is only 1/10 of a magnitude. This is near the limits of detectability for naked eye observers. Only 4 or 5 naked eye observations could be made in the time interval close to the minimum. The next 4 sections describe features of the APT that make it robust and accurate. These are the pinhole, the drive system, centering a star, and spiral search. Father and I wrote a detailed 3-part paper about the APT. Full details are in the description below. The pinhole. A pinhole is needed because measuring a star also measures the surrounding sky. In addition, we must take a reading of empty sky near the star. Subtracting this gives an accurate estimate of the light coming from the star alone. The pinhole should be as small as possible. Our APT's pinhole. Just a reminder that there are 360 degrees in a circle, 60 arc minutes in each degree, and 60 arc seconds in each arc minute. Our pinhole is 1 arc minute in diameter, and for our telescope this corresponds to a physical diameter of only 1/4 millimeter. We must be able to reliably center each star in the pinhole with a positional accuracy of 1/50th of a millimeter, which corresponds to 5 arc seconds, or better. See the reference in the description. We can use the moon to give an intuitive idea of the angular size of the pinhole. The moon's angular diameter in the sky is about 1/2 degree. A prominent crater on the moon is Copernicus. It's marked here with the yellow circle. Taking a close-up view of Copernicus, the yellow circle corresponds to the 1 arc minute view through the pinhole. The red circle relative to the yellow shows the accuracy with which a star must be centered in the pinhole. My father designed essentially identical friction roller drive systems for both right ascension, shown here, and also for declination. Rollers are much easier to make accurately rather than using gears or other alternatives. The stepper motor goes here, and this is the drive shaft of the stepper motor. Blue shows the final roller of the drive system. The gear reduction between these points is 144:1. The final reduction is made by the 76 centimeter diameter hour circle, which supports the forks of the telescope. One step of the stepper motor moves the polar axis by 1.5 arc seconds. The rollers are pressed into close contact with one another by leaf springs. The first pushes the motor shaft against a roller. Here's another leaf spring. And another. Tightening nut end disengages the drive system, allowing the telescope to move freely during setup. The reference describes the 2-month testing period of these drives. Here are a couple of subtleties about programming the drive system. The references give further information. Centering. First, the telescope moves to the nominal star position. The star should be somewhere in the pinhole. A half-second reading is taken to confirm this. It must be centered, otherwise the telescope will gradually get out of alignment with the stars, and the observing run will end in failure. The centering process is as follows. The telescope moves 1/10 of the pinhole diameter in the direction of increasing right ascension. It takes another peep to confirm that the star is still in the pinhole. The APT continues in this manner until the star is no longer in the pinhole. The APT then moves back to the nominal star position. It follows the same procedure in the opposite direction until the star is no longer in the pinhole. The telescope moves to the midpoint between the locations where the star disappeared. The APT is now centered in right ascension. The same procedure then takes place in declination. The star is now within 5 arc-seconds of the center of the pinhole. The entirety of centering takes only 10 seconds. Suppose that all is dark within the pinhole when the APT first moves to the star's nominal position. Then a spiral search must be executed to find the star, otherwise the observing session would have to be abandoned. This shows the first 2 spirals of a spiral search. The search succeeds if the star is found in the pinhole and it is successfully centered. This ensures the APT isn't misdirected to a patch of mist. A spiral search also fails if the star isn't found after 4 spirals, marked by the boundary of the diagram. In this event, the APT sleeps for 10 minutes, just tracking the rotation of the Earth, before attempting to resume observations. A full spiral search takes 1 minute to complete, but very often a star will be found within the first spiral, which takes 7 seconds. The APT was situated in my father's back garden in Bexley Heath in the suburbs of London. This affected the telescope's limiting magnitude, but apart from this, excellent results could be obtained. My father died 2 years after the APT's first light. After this, the APT was loaned to Crayford Manor House Astronomical Society and relocated to a much better rural site outside the village of Trottiscliffe. Here, the APT produced exceptional results for another 8 years. It was operational for a decade. See the description for credits, corrections, references, etc. Many thanks for watching.